Greetings and welcome to another episode of Neural Network Arena, where algorithms duke it out and only the fittest survive. I'm your boy Simpleton, here to keep it simple with the Simpletron. Today we're soaring into new heights with a battle that'll ruffle some feathers. We're talking about bias, and no, not the kind that'll get you canceled on Twitter. To really let us dig into the impact, we'll do a double header with two different types of training data. This will really let us see exactly how bias impacts the results. In the left corner, streamlined and ready for action, we have the Simpletron Blackbird. Inspired by Lockheed's supersonic jet and Honda's record-breaking motorcycle, this neural network keeps it simple with no bias parameter. Will less be more? We're going to find out. In the right corner meets Simpletron Hayabusa. Inspired by Suzuki's Speed Demon, this neural network has a bias parameter. Why did Suzuki name this bike Hayabusa? I'll give you a hint. Blackbird is the favorite snack of the peregrine falcon, and as you may have guessed, Hayabusa is how you say peregrine falcon in Japanese. Now, when we say bias, we are not talking about your uncle's questionable Facebook posts. The current thinking is that it allows a neural network to find a better decision boundary. What our tests show is that it's a lot more nuanced than that. If you recall from our earlier videos, a classification neural network, that is trying to find if something's in one class or the other, tries to find a decision boundary. And this decision boundary, because we only have one neuron, can only be a straight line. Let's look at how the weight and the bias affect this line. When you change the weight, it changes the slope of this line, as you can see. You'll notice that even though the slope of the line is changing, it's locked at that origin of 0, 0. On the other hand, if you change the bias, it changes the y-intercept of the line. In other words, it moves it up and down. Let's take a look at how changing the bias affects the decision boundary. It moves it up like that and down like that. So you can see it's actually moving it here up to where there would be some of these that would no longer be classified. But that's why it's got both, so that I can put this line anywhere it wants in this two-dimensional space. Again, because it's only one neuron, at the moment it has to be a straight line. Down the road, we'll get to more fancy things where we can have all sorts of curves in this line. But here's where my experiments didn't line up with what I was learning in class. This graph having two dimensions means it also has two inputs. For example, it could be credit score on the x-axis, annual income on the y-axis. That part we agree on. Where we diverge is, to start simple, our model only has one input, credit score. Hence, it only has an x-axis. With just one axis, it's able to set that correct decision boundary with weight alone, no bias needed. Let's take a look at it on this graph. The formula for prediction is shown at the top left. If input times weight is greater than or equal to zero point 0.5, we predict the customer will pay. This zero point 0.5 is our decision boundary. In this example, we're using credit scores ranging from 1 to 100 as our input. These scores represent the percentage chance a customer will pay. The table on the left shows different weights and how they interact with various credit scores. The cells are color coded, red for did not pay predictions and green for paid predictions. The highlighted row with the weight of 0.01 is crucial. This is our optimal weight for our model. Why? Because 0.01 times 50, the middle credit score, equals zero point 0.5, our decision boundary. With this weight, that credit score of 50, the graph on the right visualizes this concept. The vertical dashed line at zero point 0.5 represents our decision boundary. To the left are red dots for did not pay, and to the right are green dots for paid. It's important to note there's only one input, only an x-axis. The y-axis on this graph is there just for visualization purposes. It doesn't actually represent a dimension in our model. There's no y-intercept, and since bias changes the y-intercept, and we don't have a y-axis, bias really isn't necessary. All right, so let's just jump right into the code here. This is the template. Go through this real fast. And when it initializes, it sets the default weight and learning rate in the superclass. You can override that if you're doing something different with the model that you don't want to use those, but it's nice to keep them the same because that way any difference that you see, you know, is attributed to something else, not, oh, I had a learning rate of this in one and that in another, right? Train, this is the heart, this is what the engine actually calls. It passes in the training data and it basically loops through each epoch. Now, an epoch is running through all your training data once. And so it says run an epoch, and that's exactly what running an epoch does. It loops through all the training data. For our training data, we've got one input and one output. We've got a credit score and did they pay the loan or not. So that's what it passes into training iteration. Training iteration, it does three simple steps. First, it makes a guess. This is the credit score. Do I think they paid? Do I think they didn't pay? Second, it checks the guess. If it's wrong, it looks at how much, and we call that the loss. And then finally, it adjusts the weight based on what that loss is. We actually call adjust weight, get an adjustment, and then we take our current weight plus the adjustment and store that new weight. Let's do the Blackbird first. So the Blackbird was just like this. So we can simply copy this, paste this in, call it Blackbird. And the only thing we do have to do is remember to name this class the same as the file. That's how the engine's able to find it, is the file and having the same name as the class. Now we'll do the Hayabusa. So let's paste and create the Hayabusa. Oops. And we're going to update that class name. And let's take a quick look at what we need to do to add bias. This breaks down into 5 steps. We're going to create a variable called bias, start it out at 0. Then in that training iteration sub, we're going to create a variable called new bias, just like we had new weight. Then we're going to also add those to record iteration so that we can see the results afterwards if we're trying to figure out what's going on. And then just like we updated the weight to the new weight, we're going to update the bias to the new bias. Then the last thing we need to do is when we're making our prediction, we have to factor in the bias to that prediction. Prediction, take the credit score times the weight. This is just rounding it to 7 decimal places so that we don't get rounding errors. But if the credit score times the weight is greater than 0.5, then we predict true, otherwise false. Here's where we're calculating our loss, and here's how we're adjusting our weight. Not the way ChatGPT, Claude, Perplexity says we should either, but the way that works better. So, did we name the thing Hayabusa? We did. So let's go ahead and we'll add. You know what? We don't need all these comments here, but what we are going to do is say self.bias equals 0, and then yeah, it's trying because I don't have 2 spaces. All right, and down in here, new bias. All right. Now, our final step in this process is to add it to this prediction. So we're going to say credit score times weight and plus the bias. Now, oops, I guess self.bias. There we go. That should do the trick. So let's go and run these against each other in our arena here. So we've got the template Simpletron. We've got the Honda Blackbird and the Suzuki Hayabusa, my dream motorcycle, just by the way. I ride a Harley, but when I was a kid, I dreamed about this one. So, in any case, I think that should be ready to go. Let's see, cross your fingers. Hopefully, we don't have any issues. Let's see what happened. All right, good. They all ran, and let's take a look here. So the template matches the Blackbird. That's no surprise. That's because it was just a straight copy. And the Hayabusa with the bias is scoring slightly higher, about 0.5% higher there. This is not a big shock to me at the moment because the current training pit we have, the data algorithm we're using, I was expecting it to cross through the origin, so we didn't need the bias, which would shift it up or down like that. We just naturally use a bias of 0. So the next step was to go to a training pit, and here's a training pit that creates our the data that we're using. It generates a credit score, random from 1 to 100. And then if we include anomalies, which we do, because if we don't, then it just will get 100% because it finds that decision boundary very easily, and it holds true. But if we include anomalies, it says, hey, whatever that percentage is, whatever that credit score is, 1 to 100, that's the percent chance they have of paying this off. So if it's 75 credit score, that means there's a 75% chance it'll get paid off, and it returns a true 3 out of 4 times. But I did think that was kind of neutral, as did all of the large language models I've been consulting about this. So I went out to ChatGPT and Claude and Perplexity and said, how do I alter this to show the impact of bias? They all came back with the same answer. Basically, all they did is they added a shift to it, an offset. In this case, they scaled it. But and then I said, hey, I want you to really show the emphasis of bias because I'm just not seeing it. They said, no problem, we can do that. And then in this one, it they altered it even more. And here's another one. All of these have basically the same impact. Let me go ahead and copy the name of this here. And let's go back to the arena and change our training pit to bias emphasis. And let's see if now that we're trying to emphasize the benefit of that bias, if it does. You know what, we can take that one out. But by the way, we're running 100 epochs with 3,000 sample data. And what do we have here? Oh, look, still just a little bit difference. Only 27 basis points in this case. Well, what's going on? Did that LLM not understand it? Did that one not understand it? Should we try this one? Same thing. Take a look. And with only 3,000, look. Oh, in this case, it did a little bit worse. That does. Oh no, it did a little bit better. Look, about 27 basis points again. And actually, I took it from 3,000 out to 300,000 just so that the law of large numbers would really hone in on exactly what that is, because you can see every time we run it, there's a little bit of difference in there with just using 3,000. Right here, numbers are changing, bounce around a little. It basically, no matter what, averages up to 25 basis points. So what's going on here? It really threw me for a loop because my expectation was when we switched from the normal 50 is the baseline to shifting that number up. Actually, I'll show you all of them now. Um, I also, while I was trying to figure out why there was no change going on, um, let's get rid of this one and let's put these other ones back in, right? So here's the one from ChatGPT that's supposed to use bias. Here's the one from Claude that's supposed to use bias. Claude, it took 3 times because we started discussing some crazy in-depth issues. And then here's perplexity. Let's see how all of these compare to each other. All right, so this is just our straight up template, and like before, it's about, this time a little bit less, only 13 basis points, but still very, very close. ChatGPT did it the same way that we did. Claude, you can see here, got it a little bit better. It's interesting. Sometimes it's a little better, and sometimes that's worse. And then Perplexities really took a nosedive here, and these results are pretty consistent. If we run it again, we're going to see about the same thing. Let's look at ChatGPT. So when you look at ChatGPTs, there's one little problem here. Nah, best yet, let's leave and look at Perplexity. All right, so when we look at Perplexity, there's one little problem. So first off, the reason that their numbers tank is because they insist on putting this star input uh, at the end of this weight adjustment. They say that that makes it gradient descent, but I'll tell you what, it makes the numbers worse, that's for sure. Now, is there a situation where maybe it's better and because we only have one input? Yeah, but I don't think so. It really doesn't make sense to put that there. We'll get into gradient descent another day, but it's that. The problem I had is that these two are locked together. Either they both go positive based on the law. If the loss is positive, then they both go positive. If the loss is negative, then they both go negative. We go back to our decision boundary here. Remember, This makes it go up and down. When you hit the bias, it moves the whole thing up. So it seems to me that you might have a scenario where you needed to go positive on the weight and negative on the bias, but not one model allows for that to happen. And so in discussing with Claude, Claude came up with a little bit different of a bias. Um, the loss and also how far the input is from the decision boundary. And because of that, it's a little bit more accurate um, most of the time. And again, perplexity using gradient descent. In any case, so so that's pretty much what we've got in the code here. Kind of anticlimactic, but unlike what all the theory said, bias is going to make a big impact if the decision boundary does not cross the origin 0, 0. It was not true. It made freaking almost no impact at all. Now, I do think when we start using two inputs, we will see some benefit there. But I do also question what happens when we go to three. Is ChatGPT really right that it will work just fine the same way it works with two? I don't know. We'll find out. That's the whole point. We like testing this stuff. So, in summary, with only one input, bias has a very tiny benefit, about a quarter of a percent. But if weight alone can find the decision boundary, then why does it even have this very tiny benefit? Because it's also very consistent. It's almost never the other way. So there's something there, but what is it? If you know, please leave a comment. I would love to understand, and I have been putting a lot of time into trying to figure that out and coming up flat. Why is it 0.25 better? It seems to me like they should be even. Uh, Now, next, of all the methods I've seen, they're all quote unquote sign locked. In other words, both the bias and the weight move positive or they both move negative, but one never goes one way and another the other. I haven't found a situation where that's a problem, but I do think it's worth at least keeping our eye on because maybe at some point we do come across a situation where that might be useful. And then the last thing is that the change going from 1D, where you've got a point on a line, and that's the decision boundary, to 2D, where it's a line in a plane being the decision boundary, and that line is controlled by a weight for the slope and a bias for the y-intercept, to 3D, where it's a plane in a 3D space being the decision boundary, and now the weights control the orientation and the bias also allows it to move. It just feels like it's a little bit of an inconsistent pattern going. I would have expected the same change you apply from 1D to 2D is applied from 2D to 3D, and maybe it is, but I can't quite get there on that. So we'll keep an eye on that as well. And then last but not least, we are not fans of gradient descent. Uh, okay, so the winner is, and it was a close one because the Hayabusa does go a teeny bit faster at the expense of the bias. So we're going to call the Honda Blackbird the winner. No bias if you only have one dimension. Coming up next time, we'll have rock stars of machine learning, how activation functions shred neural networks. We'll talk about when and why to use which activation function. We'll show you the logic for all of them. We'll have different arenas that highlight the benefits of one over another, or potentially show when you would use this versus using that. It should be a great show, so please join me. Also, please tell me if I'm full of baloney. I make a lot of mistakes, and if you think I'm wrong, you're probably right. So let me know. Or share any other thoughts you'd like to share. I'd love to see what you're thinking. And if you enjoyed the video, please subscribe. Thank you so much. Peace.